All right, first problem for today. A team of biologists have discovered a new creature in the rainforest. They note the temperature of the animal appears to vary sinusoidally over time. A maximum temperature of 120 degrees occurs 5 minutes after they start their examination. A minimum temperature of 100 degrees occurs 14 minutes after the maximum temperature was recorded. The team would like to find a way to predict the animal's temperature over time in minutes. Okay, create an equation in the form, blah, 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 for the temperature as a function of time in minutes. Let t equals 0 represent the time at which they begin their examination. All right, so I'm going to scale out an x-axis here. T equals 0 is when they start the examination, and we have to go up to at least 14 minutes after the maximum, 5 minutes, so we're looking at least 20 in terms of how much we need for our x-axis here. So if we start with 0, let's see, 2, 4, 6, 8, oops, that's not right, 8, 10, 12, 14, 16, 18, 20. So this will work. All right, now we need a y-axis. We're looking at values that range in the 100 to 120 neighborhood here. So if I say, put a break in the scale here, make this 100, 102, 104, 106, 108, 110. Will that work? I think that will not quite fit. Let's go 5, 10. You'll see 105, 110, 115, 120. We'll go with that. All right, let's start plotting some points here. A maximum temperature of 120 degrees occurs 5 minutes after they start the examination. So there's the 5 minutes, and the 120 is going to be a maximum. A minimum temperature of 100 degrees occurs 14 minutes after the maximum, so that would be at 19. So 100 degrees is going to be at 19 here. So this is the top of the sine wave. This is the bottom of the sine wave. All right, halfway between the 5 and the 19, 5 plus 19 is 24, so that will happen at 12. So at 12, we need to be halfway between the maximum and the minimum. So it's going to go like this. And what do we have here? We have from 12 to 19 is 7 spaces, or 7 units. So I guess we did need a little bit more space coming this way. So 19 plus 7 would be 26. So we get 21, 22, 23, 24, 25, 26. So that's going to be right here. And then we're going to go 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7 is over here. So we're looking like that for a sine wave. Now, one thing that's helpful with these guys sometimes is to draw in that midline, like that. All right, let's label these points. So that's at 5, 120. This is at 12, 110. This is at 19, 100. This is at 26, 100. And then over here, we're at -2, 110. All right, now we need an equation, and y equals a sine b t minus c plus d. All right, so the a, that's going to come from the amplitude. we have a maximum of 120, a minimum of 100. That's a total distance of 20. The amplitude will be half that, so 10. Just to relate that, if you're looking at a regular sine wave before any transformations occur, it goes from positive 1 to negative 1. So the total distance is 2. Half the total distance would be 1, the 1 sine of x. All right. The b is going to come from the period. The base period of 2 pi has to get divided by the b term, and that gives us the period of the graph. So one full period goes from here to here. So from a negative 2 to a positive 26 is 28 total spaces, or 28 units. So it'll be 2 pi rather, divided by 28. Oops, I'm sorry. Didn't see I was off the page there. 28, we can trade these two as a shortcut. That makes the b pi over 14. All right, I'm going to skip over the c for a moment and concentrate on d. To identify the d, the easiest thing to do is to think of the original midline from a sine wave before any transformations occur is the x-axis. That's now up at 110. So the last piece of information we need is the c term. Okay, that's going to affect the horizontal shift, and as long as the b term is factored out in this algebraic structure, we don't have to worry about the c divided by b thing. It's just how do we have to shift it and in which direction. So one way that we could shift it would be this right here. So the original sine wave would have been having its origin here. It moved 2 to the left, so we'd make that a plus 2. With the last tweaking of that c term there typically are several options of what you could do in order to get the shift. Rather than thinking of the shift going this way, what we could have done is thought about the shift going all the way over there. So we could have replaced that with a minus 12, but then if sine wave would be heading down, we'd have to put a negative sign in front. So that's a little bit more inconvenient. This is definitely the cleaner of the two options. Actually, it said function notation, f of t, not y. All right, so the amplitude has to be 10. There are no other alternatives. That b term has to be pi over 14. There are no other alternatives. The 110 has to be the vertical shift. There are no other alternatives. This could be different, but changing that could change the SIGN of that in front. But this would be the cleanest of the options. Okay, the other things they're asking us for. Use your model to predict the temperature of the creature at the time they started timing. Okay, at the time they started timing would be when t is equal to 0. So we'll just be plugging 0 into this equation, and then that would be something you would type in your calculator. You wouldn't be expected to do that using mental math. We expect, based on my sketch here, to be somewhere in that like 115 range, but that's just a very rough sketch in order to be able to piece this stuff together. We're certainly not going to rely upon that as our answer. We'd have to plug that in. It does turn out that after you plug that into your calculator, part B turns out to be about 114.3 degrees. So the 115 isn't that bad of an estimate. All right, number 2, get that centered there, get a clean piece of graph paper. A group of students are studying the sinusoidal nature of tides. The values for the depth of the water level were recorded at various times. At t is equal to 2 hours, low tide was recorded at a depth of 1.8. At t is equal to 8 hours, high tide was recorded at a depth of 3.6 meters. Part A, create a function in the form blah, 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 the same algebraic structure as from number 1, for the tide depth as a function of time in hours. All right, so for time-wise, we're talking about going from 2 hours to 8 hours, so we have to at least minimally show that. And if last problem was any indicator, we probably even need more room after that. So let's see, if we make that, say 2, 4, 6, 8, it's a little scrunch, but I think that'll work. And that'll leave us room to extend the pattern over there. And the depths here that we're looking at, we're going from 1.8 to 3.6. So we're not going to be able to sketch those exactly, but we can get rough estimates. So let's make this, say, 1, 2, 3, 4, 5. I'm thinking that'll probably get the job done. So at time is equal to 2 hours, we're at 1.8. So at 2, 1.8 is roughly in that neighborhood right there. At t is equal to 8 hours, we're at 3.6. So that's roughly about there. So this is low tide, that's high tide. So we're doing roughly like this here is what we're looking at. So the middle of the 2 and the 8 would be 5. And then halfway between 1.8 and 3.6, let me write these numbers in here. So the average of 8 and 8.6 is 2.7. So roughly in this neighborhood right here is going to be 5, 2.7. So we need an equally spaced thing over here. So 1, 2, 3, 1, 2, 3, up to about here. That's going to be the point -1, positive 2.7. And then 1, 2, 3 puts us there. That's going to be 6, 7, 8, 9, 10. Something doesn't look right there. 9, 10, it's 11. Okay, 1, 2, 3 spaces, 1, 2, 3 spaces. Doing this, that's going to be 11, 2.7, and this is the midline going through there. All right, so that's probably enough information in order to get our equation. They're specific in the form they want us to use. F of t is equal to a sine b t minus c plus d. All right, there's not necessarily any order that you have to attack these in terms of what you want to fill in. Usually the c is best saved for the end, but in terms of the a, b, and d, I don't think it really matters. Okay, the A is going to come from the amplitude. That's going to be half the distance from the bottom to the top. Okay, half the distance from the bottom to the top turns out to be about 0.9. Well, 0.9, not about. Two pi divided by the b term has to give us the total period of the graph. So we went from a -1 to a positive 11. That defines one full period of the graph. -1 to positive 11 is a grand total of 12. So 2 pi over 12 equals b. B is pi over 6. I'm saving the c for the end. The d is going to correspond to that shifting of the midline, which starts at 0, which is now up at 2.7. All right, what I'm going to use for my point of reference with the shift is this right here. Originally, that we could think of as there, slid over to the right. So that would make this a -5. The one that's actually closer would be this one right here, but that would cause it to go down, so we'd have to make a tweaking for that. So the other alternative equation we could write would be this guy right here. If you check them on your calculator, if you so desired, you would realize that they both produce the same graph. It's just two different ways to get to the same value. Whether we think of that as the original origin that got shifted right from there, or that as the origin that got shifted left, it's both are valid. It's just a question of here you'd have to adjust with the graph coming down instead of going up. All right, what else are they asking us for? Give the depth of the water at T is equal to 21 hours. So we'd plug 21 into this equation. That would not be anything that you'd be expected to do by hand. That would be something you would just use your calculator for. And that depth turns out to be about 3.5 meters. All right, that's number 2. On to number 3. Right there looks pretty good. The population of dragonflies on a small puddle in the San Antonio River varies sinusoidally with time. On October 4th, the population was at its maximum of 3,200. On October 14th, it was at a minimum of 600. Create a function in the form, same algebraic structure, for the population as a function of time in days. Let t equals 1 represent October 1st. So our x-axis, we have t equals 1 as October 1st. We have October 4th. We have October 14th. So we have to have a scaling that at least gets us to the 14th. Based on the last couple of examples, we probably want some more space to the right as well. So let's scale out an x-axis here. And we'll go 1, 2, 3, 4 is a key number. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And this leaves me some space to the right to continue the pattern. All right, now we need a y-axis. So we're looking at y values of 600 and 3,200. So we need some kind of scaling that would make sense with that. What if we go like 200, 400, 600? Does that leave us enough room up top? So it'll be 8, 10, 12, 14, 16, 18, 20, 22, 24. Ugh. So I did leave myself enough room here if we do that scaling. So what if we do, say, 500, and every other one will be 1,000. So we'll do 1,000, 1,500, 2,000, 2,500, 3,000, and then this would be 3,500, and that would leave us enough room to hit the 32. Okay, that's what we'll have to go with the where I chose to draw the graph on the graph paper here. So on October 4th, it was a maximum of 3,200. So October 4th, 3,200 is in this neighborhood right here. So that's a 0.4, 3,200. On October 14th, it was a minimum of 600, which would be right about here. So it's 14,600. So that's the maximum. This is the minimum. We've got to get that point dead in the middle. Halfway between 4 and 14, well, 4 plus 14 is 18. Half of 18 is 9. So 5, 6, 7, 8, 9. And then halfway between 600 and 3,200, so 3,200 plus 600 is 1,800. Half of 1,800 is 1,900. So the midline is going to be just below there. So that's going to be at 9. Did I say 1,800? 1,900. I don't remember what I just said. 1,900 is correct. So it's going like this and like this. So 1, 2, 3, 4, 5 spaces. 1, 2, 3, 4, 5 spaces. 1, 2, 3, 4, 5 spaces. Right here. That's going to be 14 plus 5, which is 19. 1900. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Puts us over here. So this is going to be negative 1, 1900. All right, that should be enough information. F of t is equal to A sine bt minus c plus d. Normally, you want to save c to the end because there's multiple options that you could do. My personal preference is I want to get A, B, and D done first. Which order you do A, B, and D really doesn't matter. In the end, it's all going to be the same, but usually easier to save C for the end. All right, so the total distance from 600 to 3200, 6 to 32 is 26, so 2600 cut in half would be 1300. All right, here to here, from the negative 1 to the positive 19, represents one full period. So that's a total of 20 spaces. So 2 pi divided by b has to give us 20. 2 pi over 20 is going to be b. b must be pi over 10. Saving c to the end. The d corresponds to that midline that's shifted up to 1900. Now we need to see. The easiest thing I think to think of would be this shifting to there, which would make it a plus 1. That would be the cleanest, quickest equation to get. All right, another alternative is you could think of the shifting coming this way, which would cause the 1300 to be negative. And that would correspond to a 9 in the opposite direction. So those would be two different equations that would produce the same result in the end. It would be your call in terms of which you would prefer. On a quiz or a test, they would both be full credit. All right, part B, use your model to approximate the number of dragonflies on October 28th. So that would be plugging 28 into this equation. When you plug 28 into the equation, you end up getting about 2,301 dragonflies. And again, plugging that in, that's a calculator problem. You wouldn't be expected to do that by hand. All right. For the homework tonight, there is going to be one side of the page that are similar questions to this. I'm sorry, I didn't see that again. Similar questions to these guys. And then the other side of the page is going to talk about a couple of things that I want to clarify to make sure you're okay with the terms. One has to do with increasing, decreasing. If you're on a part of the graph that's going up, the graph is considered to be increasing at that value. If you're on a part of the graph that's going down, the graph is considered to be decreasing at that value. So in terms of what I have drawing here, the graph is increasing from negative 1 to positive 4. It has a maximum at positive 4. It's decreasing from 4 to 14 with a minimum at 14. It's increasing from 14 to 19, and that 19 number we'll talk about in a second. Okay, that's kind of common sense. That's not anything that really necessitates an example. The next thing might be to you. One of the things we're going to be talking about as we move through the course, the concavity of a graph. Okay, in this neighborhood, the graph is concave up. Thinking about it, if you poured water in there, it would hold water. This part of the graph, it's concave down. It would not hold water. Somewhere between concave down and concave up, it must change concavity. That's going to happen right here. That's known as a point of inflection. So we have a point of inflection at 1900 because of the fact of that's the place where it changes concavity from concave down to concave up. Now increasing, decreasing, mins, maxes, concave up, concave down, points of inflection, Those are really big deals in calculus, and you are going to learn calculus ways of identifying those particular features of a graph next year when you get there. For right now, it's just visual inspection. So for example, whatever this point is right here, that random location on the graph, I know that at that value, the graph is increasing because it's going up, and it's concave up because it's at a point of the graph where it would visually appear to hold water. So those are some general things that you need to know for tonight's assignment, in addition to the examples of writing the sinusoidal equations that I just went through.